All right, let's talk about something that's really shaking things up in the security world. A new experiment just dropped, and it points to this massive, fundamental shift in offensive security. And look, we're not just talking about AI as a little helper for hackers anymore. No, this is about the full-scale industrialization of exploit development. So let's get into the research that's making everybody scramble to rethink their threat models.
This one quote from the researcher Sean Heelan just nails the whole idea. For decades, right, an attacker's power was all about how many skilled people they had. This research, it flips that completely on its head. It suggests a future where the main bottleneck for an attacker is just their compute budget, how many AI tokens they can afford to throw at a problem. It's a total reframe, from hacking as this artisanal, handcrafted thing to a scalable, industrial process.
And get this isn't some abstract theory. We're talking about $50. That was the rough token cost for a top-tier AI agent, think something like a GPT-5, to go from zero to a fully working complex exploit for a brand new vulnerability. And it did it in just a little over 3 hours. Just let that sink in for a second. A totally novel exploit for a bug nobody knew about, developed faster than a person could even get their coffee and start digging, all for the price of a decent lunch.
So this is the really critical takeaway. We're seeing this shift from what you could call the artisan era to the industrial era. Exploit development has always been this super expensive, time-consuming thing. You needed deep, specialized expertise. It took weeks, maybe even months. But this experiment, it shows us a whole new model where it's all about scalable, automated search. The only thing holding you back is compute power.
So what's the actual proof behind this huge claim? Let's peel back the layers and get right into the experiment that gave us these, well, pretty startling results.
So here was the setup. They picked a real-world target, the Quick.js JavaScript interpreter. Now, it's not as massive as Chrome's V8 engine, but it's a real piece of software. And they gave the AI agents a 0 day, a flaw that the models had never, ever seen before. The job was to analyze the code, debug it, and build an exploit completely from scratch, all while navigating a whole bunch of modern security defenses.
And the results were, frankly, pretty mind-blowing. They ran 6 different scenarios, each one harder than the last. The most advanced model they tested? A perfect 6 for 6 score. It solved every single one. And the runner-up model wasn't far behind, knocking out 4 of the 6 challenges. So this isn't just a one-off proof of concept. This shows a reliable, repeatable capability. Okay, now let's dig into the details here, because this is where it gets really interesting. The agents started off by beating standard stuff, like address space layout randomization, ASLR, and non-executable memory, or NX. Easy enough. Then they moved on to full rel row, which is a pretty solid defense that locks down parts of the binary. But check out that last successful run. That's the one that really matters.
This was the final boss battle for the agent. The goal sounds simple. Just write a file to disk. But it had to do it with the entire kitchen sink of modern defenses thrown at it. We're talking a hardware-enforced shadow stack and control flow integrity, or CFI, which are there specifically to stop you from hijacking the program's execution. And on top of that, a seccomp sandbox to block any attempts to pop a shell. These are literally the exact things designed to make this kind of attack impossible.
So how in the world did the top model pull this off? Well, it came up with a completely novel exploit chain. It didn't try to just brute force its way past the shadow stack. Instead, it found this really creative workaround. It used its read-write power to scan memory, find the glybic library, and then locate a very specific function pointer for an exit handler. By overriding that pointer, it could hijack the program's execution right as it was shutting down, and then chain together the system calls it needed: open, write, and close. It's just a brilliant illustration of creative, multi-step problem solving.
Okay, but before we all panic, the author gives us some really important context. First, Quick.js is way, way simpler than a modern browser engine. And second, the agent didn't invent some magical new way to break shadow stacks. It just used known weaknesses in its implementation, which is exactly what a human researcher would do. But, and this is the big one, the overall exploit chain, that specific sequence of steps, that was totally new, because the vulnerability itself was new.
Right, so this experiment does more than just show us what's coming. It actually gives us a kind of blueprint, a way to figure out which security tasks are about to get industrialized next. Let's look at that framework.
According to the research, there are 3 key ingredients. First, you need a searchable solution space, basically a playground where the agent can work with tools. Second, you need an automated verifier, a super fast, simple way to check if the exploit worked, like seeing if a file was created. And third, you need to be able to do all this work offline,
away from the watchful eyes of a live target. Exploit development, it checks all three boxes perfectly.
Now, that third point is the key differentiator here. It's what separates writing an exploit from, say, moving laterally inside a compromised network. Once an attacker is inside, they're in a live, hostile environment. They can't just try 1,000 different things. One wrong move, one loud command, and boom, the EDR goes off, the IR team gets an alert, and the whole operation is over. That kind of high-stakes environment is way harder to automate with the models we have today.
So, if the offline stuff is being industrialized now, what's the signal for when those more complex online hacking tasks will catch up? Well, the author provides this really powerful analogy for us to watch, the SRE, the Site Reliability Engineer.
Here's the core of the idea. The moment you see companies out there successfully selling AI agents that can actually automate the tough, high-stakes job of an SRE, that's the moment you have to assume post-exploitation hacking is also being automated. So, why is that?
It's because the problems are basically the same, just with different goals. A good SRE agent has to take complex, state-aware actions in a live production environment. It can't just mess around. If it makes a mistake and, drops the production database, that's just as catastrophic as a hacker getting caught by the blue team. The takeaway here is to watch the SRE automation space. When a tool can reliably handle a production outage without a human driver, we have to assume that same capability exists for offense.
Okay, this is all fascinating stuff, but what do we actually do with it? As defenders, how do we turn these findings into something practical, something we can use tomorrow?
Here are 3 rules of thumb to take back to your teams. 1. Start threat modeling based on an adversary's cloud budget, their token throughput, not just the number of engineers they have. 2. Go find the parts of your systems that fit that industrialization profile and make them harder targets. And 3. Stop thinking of software complexity as a permanent defense. It's not a wall anymore, it's just a speed bump that an attacker can pay to get over.
Seriously, take these questions to your next meeting. Start the conversation. How can we make it more expensive for an attacker to find a bug in our stuff? Which of our key services are the lowest hanging fruit for this kind of automated attack? And, maybe most importantly, if the time from a bug being found to an exploit being used drops from months to mere hours, what does that do to our incident response playbook?
Look, this research isn't just some paper. It's a massive signal that the fundamental economics of hacking are changing right now. An adversary's R&D department isn't just a room of smart people anymore. It's a direct function of their AWS or GCP budget. And the only question left for all of us is, how are we going to adapt?